Okay, we're going to look at odd and even functions. We've got a parabola here, y equals x squared plus 3. So let's have a look at f of 1 equals 4 here. Okay, and the key point that we're going to explore with even functions is they're symmetrical about the y-axis. So that means that the y-axis is an axis of symmetry. That's not a very good line, but you got the idea. So the y-axis is an axis of symmetry. So let's have a look at 1, 4 here. That's this point there. 1, 4. And let's look at the mirror point, minus 1, 4. There we go. Okay, so we're looking at these 2 points, and we're going to compare that also to 7. And the other mirror point will be minus 2, 7. Okay, so if you look at x and then minus x, what do you notice? Well, you got the same y value, don't you, here? Yep. And same thing down here. If I look at x for the 1, what do I notice about minus x? They've got matching y values. Okay, so we can see that here. Here are my matching y values, just there. And here's the other pair of matching y values. So what I can say is, if I take any x and I take f of minus x, then I'll get the same y value. You can see that here. So f of x equals 4, f of minus x equals 4. So this works for any x value for even functions. So if I chose f of minus 3, right, that'd be equal to f of, actually let's reverse that for a minute. I'll say f of 3, that'd be f of minus 3. Okay, so this is a property of even functions, and it's true for all x values in their domain. Okay, so what are some key points? A relational function is called even if there is symmetry about the y-axis. Okay. What else? Algebraically, so graphically it's symmetrical about the y-axis, but algebraically f of x is equal to f of minus x. So if you can show that that is true for a function, then you can say that it's definitely even. Then more generally, a relation is even if its equation is unchanged when x is replaced by minus x. Okay, so if you look at this function up here, if I find f of minus x, what do I get? I get minus x all squared plus 3, which is equal to x squared plus 3. So you can see that last point. More generally, its equation is unchanged when x is replaced by minus x. So you can see that here. We've got, there's my original equation. Here's my f of minus x equation, and I've still got the same expression, don't I? X squared plus 3. So replacing the x with minus x gives you the same expression for even functions. Okay? So now for these examples, we're going to prove that they are even. So the first thing to do is say f of minus x equals, now you have to show all the steps here, so 3 minus x all squared plus 5, that's equal to 3x squared plus 5, which is equal to f of x. Now this is all the steps required in the working out. Now at the end of that, you can say therefore f of x is even. All right, what about this one here? Let's try a different color. So you've got f of minus x first. Right, we'll come down here a little bit. So it's minus 2 minus x to the 4 minus 5 brackets minus x to the 6 plus 1. So that's equal to minus 2x to the 4 minus 5x to the 6 plus 1, which is equal to f of x. Right? So because of that relationship, we can say therefore f of x is even. Alright, so you can see there's our original expression. There it is. And if you end up with the same expression after putting minus x in for x, then you can say f of x is even. Now let's do this one. We're going to go, let's try a different color again. We're going to have g of minus x is equal to 2. So replace all the x's with minus x. Now that gives me 2 to the x plus 2 to the minus x, which equals g of x. Therefore, g of x is even. Okay, so that's how you show algebraically that a function is even. Now what about an odd function? Well, odd functions have point symmetry. Okay, that means that you can take the function, rotate it 180 degrees about the origin, and it will map onto itself. Okay. Alternatively, you can think of it as successive reflections, the x-axis and the y-axis, which we looked at the other day, gives the same graph. Okay. So if I reflect this graph in the y-axis and then the x-axis, or vice versa, the graph will map onto itself. That's a property of an odd function. Geometrically, that means if I rotate the graph 180 degrees about the origin, the graph maps onto itself. Okay, so let's have a look at some properties here. So it says f of 2 is equal to 6. So we've got a point here to 6. And f of minus 2 is minus 6. So here's minus 2, minus 6. And if you look at that particular property there, okay, we can say that so let's just put a little arrow down here. So f of minus 2 equals minus 6 there for this pair. Now, from that, I could say, well, 6 is just f of 2, isn't it? Yep. So from that pair, I could conclude that f of minus x is equal to minus f of x, or vice versa. And you can see if you look at another pair, you'll be able to write down the same conclusion. Okay, looking at those points there. So for odd functions, f of minus x equals minus f of x. That's algebraically. Now, the important thing to note is that most functions are neither even nor odd. Okay, but some are. Right, so here's our summary for odd functions. Successive reflections in the x-axis and the y-axis gives the same graph for an odd function. Algebraically, a function is odd if f of minus x is equal to minus f of x for all x in the domain. And odd functions are point symmetric about the origin. Now that simply means that if you rotate the graph 180 degrees about the origin, it maps onto itself. Okay, so let's move on. So we're going to prove that this is an odd function. So I've got to prove this property here. This is what I'm trying to prove. So I'll start off with f of minus x. So that's minus x all cubed minus x, which is equal to minus x cubed plus x. Now if I take out the negative here as a factor, x cubed, I get that. Now x cubed minus x is just f of x, isn't it? So I've proven that f of minus x equals minus f of x. Therefore I can say f of x is odd. So that's the algebraic way of proving that a function is odd. Okay, let's do the next one. So we're going to find h of minus x first. That gives me 4 brackets minus x minus x all cubed. And then I get minus 4x there plus x cubed. And I'll take out minus as a factor. That gives me try that again. Okay, so that gives me minus, now 4x minus x cubed is h of x, isn't it? So I've proven that h of minus x equals minus h of x. So therefore I can say h of x is odd. Okay. Alright, so that's algebraically how to prove a function is even or odd. Now we can also use the properties of even or odd functions to sketch. So here it says complete the sketch, so each graph is an even function. So even functions are symmetrical about the y-axis. So I'm going to choose some mirror points here. So this is somewhere between 1 and 2. So I'll put a little point there. And there will be another mirror point over here somewhere. So sketching this so that it's symmetrical about the y-axis. That's the even function there. Same thing here. So this has got a little x-intercept on the other side, equally distant from the origin. So sketching this, so you can pause the video at any time. Right, so the graph have to be symmetrical about the axis here. Now here, probably better off getting a ruler to just draw a line and do a straight line here. Now it's got to be symmetrical, so we're looking for a point. It would help if we had a grid here. So let's just say, well, if you had a ruler you could measure that. Now, I've got a line tool here that I could use. Let me just check. I've got a ruler. Okay, so okay, can I move that? Let's see. No, it looks like the ruler's not going to help me. So we'll have to do it by hand. It looks like I don't have any line tools available on this program. Select. No. Okay. Right, so this is going to be difficult. It should, no, it's meant to be a straight line there. Let's try and get rid of that. You have to try the ruler. Alright, so we've got the ruler there, and Should be able to move that ruler. So check. No, it doesn't look like I can rotate this. Well, that's anyway, I'm going to get a straight line. I'll do it anyway. You got the idea. Okay, so now, all right. Now that's, you can see that this point here should be equidistant from the mirror point there. Okay, so you can do a better job than me because the digital rule is not rotating for me. Okay, now what about this one here? To make this even, and now here we've got a turning point, so the mirror point will be over here. There's reflecting points there. This here is another intercept, just there. Okay, so you're going to sketch this. Something like that. Digital ink's a little bit slippery, but you got the idea of that symmetrical function. So they're all even. Now, what about these ones? These are odd functions. And now, don't see any line tools at the moment on these. Maths assistant. No. So I'm going to have to, unfortunately, draw everything by hand. There's no straight line tools I can use. No. Okay, that's all right. So for this one here, for this to be a odd function, symmetric about the origin. Now, don't forget with odd functions, it's successive reflections in the x and y axis. So you can think of this. I'm going to reflect this in the y-axis first, so that'll be over here. And then reflecting the x-axis will leave that point where it is. At this point up here, if I reflect it, it's going to come across over here somewhere and then down. I'll do the next reflection. So if I'm sketching that, then I should have a turning point on the other side. That should look something like that. Okay, so there's my odd function. So remember, successive reflections in the x and y axis is equivalent to creating your odd function. So let's have a look at this one. If I'm reflecting in the y-axis first, I'm going to take this point and put it here. This point will stay where it is. This point over here will reflect there, but then I've got to reflect it down here. So just doing that again. This point will reflect across here, but then reflecting the x-axis so it stays where it is. Same with this point. However, this point here, when I reflect it across and then down, that's where it goes. So to complete that sketch to make it an odd function, whoops, try that again. Digital ink's not so good. Something like that. Okay. Now this one again, think of it as a reflection. So there's that point there. I'm going to reflect it over here. So I've reflected in the y-axis, and reflecting the x will leave it where it is. Now think of the turning point. If I reflect that in the y-axis and then reflect it in the x-axis, it should end up there. Something like that. That turning point should be a bit further over. Yep. So it should be a bit before the intercept. So if you sketch that now, that should be enough. You're going to get something like this. Alright, good enough? So remember, with odd functions, it's a successive reflections in the x-axis and the y-axis. Okay? Now, last three questions, you've got to test to see whether these are even, odd, or neither. Probably the best thing to do is to check Let's check f of minus x first. Okay, what do we get? We get 5 minus x to the 4 minus 3 minus x squared minus 7. So that gives me 5x to the 4 minus 3 x squared minus 7. And that's equal to f of x. Okay, so we can say that is an even function. All right, therefore f of x even. Yep. Now for polynomials, you probably noticed, for a polynomial, if all the powers are even, it's going to be an even function. Okay. Now, for this one, start off with f of minus x, which equals 4 minus x cubed, which equals minus 4x cubed, which equals minus f of x. Therefore, that is odd. So therefore, f of x is odd. Okay. Now, you probably knew this was odd anyway, because if you did a quick sketch of this, you know that, oops, anyway, try that again. Through the origin, yeah, so you know that it's not a function just from the sketch. Okay, all right, let's have a look at the last one. So f of minus x equals, it'll be minus x all squared minus 2 outside of minus x, which equals x squared plus 2x. Now, the thing is, there's a problem with that, isn't it? First of all, we notice that f of minus x is not equal to f of x, so it can't be even. And f of minus x, if you look at it, this is certainly not minus f of x, so not equal to minus f of x. Right? Therefore, f of x is neither odd or even. Okay, so that's it. Now, just for that last question, you wouldn't necessarily have to write this down. You could deduce it just by looking at this expression. But you would have to write down this bit here. F of x is neither odd or even.